this presentation, what we want to actually have is a combination of the two approaches, right? One more theoretical part and one more practical part, which will be presented by SoftServe. So let me start by discussing a little bit what's particular of machine learning systems. So the difference between machine learning systems and traditional systems is the way the behavior is specified, not directly in the code, but learned from the data. So if you consider a traditional system, how's the laser here? If you consider a traditional program like the one we see on the left, you have a programmer that writes a program who takes inputs and produces some outputs from these inputs. In machine learning, what happens is that there's part of the system which is not, there's a part of the system which is not written by a programmer, but instead by a computer. So the computer generates a model which is created by taking input data and expected outputs, and is actually learned. So at the core of the system, there's this model that uses data that is transformed into features to perform predictions for particular tasks. And we can actually see the models that are used in machine learning as a compiled software libraries that are put as part of a bigger system. So let's think about two workflows that are essential for producing these models. So in the first part, so where's the laser here? Ah, okay. So the first workflow is about model development. It is the initial part of the work in developing a machine learning system. And this is typically performed by the data scientists who take raw historical data, and they do extensive labor to study this data and to transform it into features, which are the characteristics that are needed by the model to actually perform their predictions. So this is the transformation into features. And then in the next step of this workflow, the data scientists also spend a lot of time selecting particular algorithms and training these algorithms with the features and fine-tuning them until they produce a trained machine learning model. So once we have developed the model, the data transformation rules and the model are sent to what is a second workflow, which is called model serving, and this is when the model is actually put into production. So into production, the model receives raw data that it hasn't seen before, and this raw data is transformed following the same rules that were established during the model development and are fed to the model that has been sent from model development. And as a result of this, the model can make predictions and give useful results. So one particularity of machine learning systems is, and we have to see this arrow, is that when the system is put into production, it is possible that the new data that is fed into the system, the characteristics of this data change from what was used to train the model. So maybe the distribution of the data changes or something that will alter the behavior of the model. Remember that the behavior depends on the data. So when these changes occur, the model stops behaving correctly, and it's necessary to refine it to have it behave again correctly. So there's two approaches for refining it. The first is an automatic approach where the model uses the new data that it's seeing and it retrains automatically to adjust to the changes. But sometimes it's not possible to perform this adjustment automatically, and it's necessary to send information about the behavior of the model in production back to the data scientists who can make adjustments or refine by adding new features or other things like that. So one thing also that is very important to consider is that these two workflows usually occur in different environments. So it may be that the data scientists are doing all their work in a cloud environment, doing all this, the data transformation, the model training, and the model that is trained is executed in a very different environment. Consider, for example, that it executes on your phone or another different device. So that we have these two potentially different environments. So historically in machine learning, the time that it has taken to perform this initial model development and passing the model to the serving phase is or has been usually long, like we're speaking about a question of months. And so the cycle has been long, but the demands of the projects require shorter times for performing this model development life cycle and refining the model. So we're the current state is that we're oriented to or going towards a more approach that is more similar to what we see in DevOps, where we continuously refine, or we want to continuously refine and deploy the models. So these contexts give us some particularities that we need to take into account when we want to architect for machine learning. And as I was mentioning, if we want to perform systematic design, we can use a method such as attribute-driven design. And typically when you design an architecture, you will select a set of drivers which are derived from the requirements that the customer give you. But in ADD, we have another type of driver which we call architectural concerns. So architectural concerns are additional aspects that are typically not specified in the requirement specification, but that the architects need to take into account to design the system. So in the rest of the presentation, I'm going to be discussing different architectural concerns that need to be considered across these two workflows to support these needs that I expressed about machine learning systems. So we will expand a little bit these two workflows, the model development and the model serving workflow, and I'm going to be discussing in detail across each one of these steps some of the concerns that are important to be able to achieve this continuous refinement, initial development and continuous refinement of the models. So the first step, which has to do with model development, is the ingestion of training data. So this is the first activity that needs to be done for model development. And some of the important concerns that are related to this activity are the collection of huge amounts of data and supporting the fast reading of this data. So these are some examples of decisions that the architects can make to support this. Like different types of ingestion mechanism or storage mechanism. Other concerns that need to be made for this step is the labeling of raw training data. So we need to label the data, and this implies selecting a particular toolkit, for example, for labeling the data. So here's some examples of that. And another potential concern for this step is the protection of the data that is used or the data that has been ingested. So maybe we need to protect the access to sensitive data. The next step is data cleansing and normalization. So the raw data that has been collected to perform model development may not be adequate initially. There may be data that is missing, there may be replications, or maybe even the distribution of the data may not be adequate for a particular model. So data scientists spend a lot of time in this activity of data cleansing and normalization and understanding the data. So as architects, what we need is to give them support so that they can perform these activities. So some of the concerns that are associated with this include providing mechanisms and APIs to support the query and visualization of the data and the ability of transforming large volumes of raw training data. So here's some decisions that can be made to support these particular concerns. The next really important activity here is feature engineering, where once we have this data, this raw data that has been cleaned and normalized, the data scientists identify features which are the essential inputs that are needed by the model to make their predictions. So some of the architectural concerns that are associated with this step include, again, the transformation of large volumes of data, but this time into features. The ability of, or the provision of mechanisms for data segregation, because the data scientists need to be able to separate the data into training, testing, and even evaluation sets for the training. And one aspect that is also very important here is the ability to store some of this information so that later on the processes can be replicated. Because as we saw, the models are continuously being developed, but at some point it may be necessary to be able to replicate the the model training activities. And if we don't store the exact configurations that we use to train a particular model, it will not be possible. So today there's new mechanisms that are appearing, such as data science version control systems, which are capable of storing all these types of informations, or strategies such as the use of a feature store, which is a data management platform, which different capabilities that are necessary to achieve this. Another very important activity and very time-consuming is the model training and selection. So here the data scientists, as I was saying, they select a particular algorithm, train, tune it, and evaluate it. So here some of the important decisions are the selection of a particular framework. So there's many frameworks to choose from, and some of the considerations that have to be made here is whether this framework will be used exclusively for model development and a different one will be used in model serving, or if it's going to be the same in model development and serving, which can help reduce the time it takes to go from one environment to the other. Other important decisions are selecting where the training will take place, because if you have sensitive data, maybe you don't want to send that data to the cloud, and you need to provide an environment and manage resources to train, tune, and evaluate the model. So some of the decisions may be to decide that you train on a single machine or in a distributed environment, whether you select to use hardware acceleration or not, and tools for resource management. And we also need to log and monitor training performance metrics. Finally, once the model has been trained and tuned, it's necessary to persist this model so that we can send it to the serving environment. So again, there are several design decisions that can be made here to support this concern. So some of the decisions involve how will we persist the model. So some of the frameworks have mechanisms that are specific so that the model is persisted here and recovered here, but we have the same framework. And there's other approaches that are independent of the framework. So the model is like PMML, where the model is stored in a representation that can be used with a different runtime in the serving environment. Other concerns involve decisions about storing the model, because the model can take a considerable amount of space. So maybe you need to have a storage mechanism that supports that. And maybe you will need to optimize the model after training if your model is going to be running in a constrained environment. So let's go now to the model serving workflow. So here again, there's different decisions that need to be made to support the serving aspects. So the first step that we have here is the ingestion of new data. So the difference between this one and this one is that here is the data that the model hasn't seen. So one of the concerns that the architect has to solve is how will this new data will be ingested? Will it be in batches, what we call batch prediction, and then the processing will be made asynchronously? Or will this be made by taking individual observations? For example, through an API or as a stream of data. So this is one important decision. Data validation and feature extraction, essentially what we want to do here is to transform the new data that has been ingested to features following the same approach that was defined during model development. So some of the important concerns here are ensuring that the data that is ingested conforms to the roles that were defined during training. So how can this be achieved? Well, one possible strategy is the usage of data schemas that were defined during development and which are used or can be used for validating the new data that is being seen. It's also important to monitor changes in input distribution so that we can know that the behavior will be altered. Again, there's concerns about transferring the data to the model. And it's also probably necessary, or for certain types of problems, to include features that come from other sources. So it may be necessary to select and query additional real-time data sources. Finally, another area of concerns is the transfer of the model and making the actual predictions. So how is the model transferred? This is another concern that needs to be addressed by the architect. So there's different approaches. It may be necessary to rewrite the model if the model development and model serving environments are totally different, or maybe it can be containerized and sent to the serving environment. Again, if we use these independent representations, we need to set up the runtimes for executing these. It may be necessary to consider strategies for rolling out or rolling back the new versions of the model. So what if we deploy a new model and we start seeing that it's not doing the correct predictions? Well, maybe we don't want to deploy to all the users simultaneously. So we can take approaches like blue-green deployment, canary testing, and some problems actually even require the possibility of serving multiple models simultaneously. So we need to take considerations, or at least be aware of all these concerns and make decisions to support multiple versions, being able to update and roll back the model. And finally, it's also another concern is the definition of where the prediction takes place. So there's at least three main approaches that we can consider. The first is what we call the local model, is where the model is predicting and retraining on the client side. For example, if you have on your phone a model that is identifying people in the picture. A remote model, this is when the model is executing on a server on the back end and the client is sending the data for prediction and retrieving the results. And there's a third approach, which is a hybrid model. An example is federated learning, where the model is predicting and retraining both on the client machine and retraining also, or taking retraining information and retraining globally on the server machine. So this is another important decision. Finally, last area of concern is serving the results. So we need to deliver and post-process the prediction results and send them to a destination. So here there's a lot of concerns that are related to monitoring, because again, since the new data can be changed, the characteristics of the new data can change, we need to be able to be aware of that and be notified so that we can go back to model development. So some of the concerns include monitoring, for example, the age of the model and its performance, when possible monitoring the predictions versus the actual values, monitoring deviations between the distributions of predicted and observed labels. We may also need to address the concern of storing prediction results so that they can be used later on for retraining, or even aggregating results from multiple models. So so as you can see, there's many concerns that need to be taken into account across these two workflows. So now I'm going to handle the microphone to my colleague Iurii, who's going to speak about case studies.
Thanks, Humberto. So once again, my name is Iurii Milovanov. I'm a director of AI and data science at SATURN. And SATURN is a software development consulting company that works for other ISV software development and enterprise companies, and we basically deliver the software for them. So you may have played or experienced our software, but it was labeled by Cisco or whatever it is. So today I'll try to share with you some of the examples from the projects that we delivered to our clients or develop for our own purposes, and I'll try to connect and highlight some of the decisions that we made that address the concern that Humberto just mentioned. So the first project that I would like to present to you was developed for one of the biggest oil and gas companies in the world in collaboration with another technology company, leading companies in developing networking hardware. And the goal of this project basically was to create a solution that will be able to process and analyze the data that is coming from the offshore IoT equipment. And if you remember the Deepwater Horizon accident, that project was partially related to that problem, because back in the days there was no solution to, so the oil and gas company, they were collecting a lot of data from the offshore facilities, right? But they were not able to analyze it in real time. So even if they want to do some sort of anomaly detection or predictive maintenance, they were able to analyze the data only when something has already happened. They were not able to do any proactive actions or understand that something bad is coming and maybe somehow react to those changes. So that was the biggest challenge that we had for this project. So that's the big data infrastructure and big data Lambda architecture was our obvious solution to design this solution, right? So I also want to mention some of the architecture drivers or requirements that we had for this solution. So once again, we got to ingest and process multidimensional time series data. And the data sources that we were dealing with for a single offshore facility, for a single platform, the amount of data that was generated daily was from 100 to 300 to 400 gigabytes per day, which is quite large stream of data. And the solution should be able to process that data and calculate some metrics and statistics and do multiple predictions for different time horizons, different windows, historical windows, and so on and so forth. There are many things should have been done in a near real-time fashion on a large stream of data. And the solution was also, one of the requirements for this solution was that the solution should be able to continuously learn from the data. Because one of the core components of this solution was the model that was trying to predict the general deviation from some expected pattern. And one of the challenges for us was how to create this solution in the most agnostic and unsupervised, how we call it in machine learning way, so that we don't have a clear definition what is normal, what is abnormal, right? We don't have some sort of hand-coded set of rules for a normal behavior, but rather we want to learn that expected pattern from the data and continuously learn it depending on different weather conditions, different operating conditions, and so on and so forth. So the solution should be continuously learned from whatever data was collected. And the initial data set that we started with was 300 gigabytes. You may assume that it's approximately a couple of days of operating, which obviously wasn't enough to create a final solution. So, and finally, the solution should be also able to expose the interface for domain experts, for analytics, to be able to visualize the data, see what are the trends in the data. So the analytics was also one of the crucial components of this solution. So now I'd like to go through each of the steps that Humberto set up in his framework, and highlight that particular solutions, particular decisions that we made to address the challenges related to that step. So first one is training data ingestion. So since we were designing a big data solution, and in particular it was some variation of Lambda architecture, of course we could have drove that picture differently, but it's primarily, in this particular setting, it primarily focused on the machine learning part, but in reality it was a Lambda architecture. So the Hadoop file system was the obvious choice for storing historical data and read it in a bulk fashion. And we used directory structure, quite simple approach to do data versioning. So basically for every day, for every hour, and for every minute, there was a folder that stored the data for that particular period of time. And we also had to create custom data conversion model that basically transformed the data from proprietary data format that we were receiving from the IoT equipment into traditional CSV data format. Next is the data cleansing and normalization step. So we selected Spark SQL and Spark data frames for analytics in order to be able to expose an interface for data scientists to play with this data, to see what are the trends in this data, what is the structure, what is the nature of this data. This is quite a crucial component at the very beginning of the projects of data scientists. They have to understand the data, they have to sort of feel the data, right, and understand its nature. And we also created, based on this initial data exploration, we created a set of batch Spark jobs that were used to do this pre-processing, basically preparing the data for training. So the next step, feature engineering. we used basically the same infrastructure that we use for data preparation and data normalization, and that's quite often the case because both steps they deal with similar challenges, with similar with the same data, right? But the key difference is that the feature engineering is something that evolves, something that changes. Data scientists may create new set of features, maybe design some new type of transformation, while data normalization, data cleansing is more or less consistent step, and once it's created, it remains the same. So, and the result of the feature engineering that data science team came up with set of transformation was stored in a CrateDB, which is a database specific to time series data, and it was exposed as SQL to use it for model training. And model training is the next step. So Spark has native machine learning capabilities within a Spark ML component. We use it, obviously. We use Yarn for resource management to be able to train it on a distributed environment in distributed fashion. And we didn't use any hardware acceleration because usually for numerical data, there is no need to apply any GPU computing or TPU computing, whatever it is. That usually comes with computer vision, speech recognition, that type of problem where we deal with a really multidimensional data such as images, right? And the result model was stored back to Hadoop file system and used for during deployment for model serving. So next is the model serving workflow. So to ingest the new data that was coming from the IoT sensor, we used Kafka as a message broker that was also used to do some initial data preprocessing and data transformation from that proprietary data format. For data visualization and feature extraction, we reuse the same type of transformation that we defined during model training, and that was one of the benefits that we got from using Spark, because in Spark you are able to use the same transformation that you created for batch jobs on streaming, in a streaming setting with a minimal amount of edits. So basically that really helped us reduce the time that it took to design this step. And model prediction was done as a set of batch Spark ML jobs scheduled every 3 minutes, because the requirement for us for near real-time prediction was 5 minutes, so 3 minutes was enough to batch jobs over every 3 minutes were enough for us to fit that, to meet that requirement. And model serving, the result that we calculated during that batch job, we stored back to CrateDB and exposed it via Impala to be able to use it in a Zoom data, which is a BI and analytics solution, to visualize the data, communicate it to the operator so they're able to see that data in real time. So what it helped us create highly scalable distributed IoT platform that leverages back in the day state-of-the-art big data and cloud technologies, be able to do real-time monitoring and prediction over that IoT streaming data. And also we created custom anomaly detection algorithm that we also published open source, and there is a scientific paper with that solution that was used to detect anomalies in an unsupervised way, as I mentioned before. So this was the first project. This particular project was delivered to one of our clients, and the next project is the project that we actually developed for our own purposes. So we call it Smart Parking, and this is a solution that we developed for our headquarters office in Lviv, Ukraine, where our headquarters office is located. And I would like to start with a short video that illustrates the solution. Hope there will be some sound.
While driving to any destination can be a hassle, parking shouldn't be. People get stressed when they waste time finding a place to park instead of getting where they need to be fast. What if it could be easier? At SoftServe, we're always looking for ways to automate processes and increase efficiency with our solutions. Here's what we came up with. Each space in the parking lot is tracked via video, which is analyzed by machine learning algorithms to detect open spots. Once the driver chooses an open parking spot, he proceeds forward. Another camera logs the car's license plate, verifying the authorized driver of the vehicle and eliminating the need for security cards or other ID verification. Finally, the driver is escorted to the open parking space without having to circle the parking lot even once. SoftServe delivers solutions-based services that make amazing experiences possible.
So you've just seen our
deliver the
headquarters
innovation
office in
quality.
Lviv. So if you visit Lviv sometime, you can actually play with or see this solution in real life. So today I would like to share with you some of the challenges that we faced with this type of problem, because this is a good example which is quite different from the previous case study that I showed you before, and I'll highlight the key kind of part that are different. So let's start with architectural drivers. Sorry. Yep, there we go. So first of all, we wanted to deploy this solution to our on-premise infrastructure. So we were not using any cloud infrastructure for this project. We wanted our solution to perform real-time prediction over the multiple video streams from the different 4K AP cameras. The solution itself should be able to process up to 5 images, or at least 5 images per second from 121 parking spots, and be able to scale if the number of spots increases. And it also should be able to support on-demand retraining and deployment. And initially, actually, we thought that we won't need to retrain our solution very often. That's actually a good story. We started this project in spring. We manually collected the initial training data set, so we basically made 200,000 pictures. We manually labeled them. We created perfect data set that showed quite a good performance, and on the training we deployed it. It worked well till autumn, and then winter came, right? In Ukraine, in winter time there is a lot of snow, and obviously our parking lot looked completely different. And apparently our solution didn't work at all, right? So we got to do a second iteration of training. We collected more data. In the winter time, we did the label again. We retrained our solution. Then it was able to recognize the empty spots in the winter time as well. So that wasn't part of an initial requirement, but that's something that we realized later on in this project. So let's go through the key steps in the model development workflow. So for model training, since we initially thought that we won't need to retrain very often, we use network file system as a storage layer for training data, and we use custom labeling tool to label the data. Although there are many different options that you can use for that. Some of them are open source, some of them are paid solution. But for this particular one, we use our custom solution for data labeling. And for data cleansing and data normalization, we design a Python-based or the data transformation pipeline written in Python. Since Python is quite strong in the computer vision field, there are plenty of different libraries that you can use to do image transformation and different type of things with images, such as split images, lens correction, so on and so forth. So we created that pipeline and incorporated it into a Docker application. We didn't have to do any feature engineering, because that's one of the things that people in computer vision community try to avoid these days. They want to solution to learn the features from the data instead of designing them manually, which actually was one of the biggest breakthroughs in computer vision. And for model training and selection, we use TensorFlow and Python job that was containerized into a RESTful application and deployed to a virtual machine that was orchestrated by Ansible. And for model persistence, we used Git repository to store the model. In particular, Microsoft's version of Git, but could be any Git repository. And Ansible was used to do GitOps, to actually do deployment in a GitOps manner so that once a new model is committed, it's immediately deployed to production. And for model serving, the workflow was a little bit different. So what we did for this solution, we created a job that was pulling the local storage on the camera every second or even less and transferring new images to what we call operational storage. And from that operational storage, there was a set of workers that were processing that, containerized workers that were processing those images and preparing them for prediction. And for prediction, we use the Dockerized TensorFlow model and a model engine that performed the prediction and sent the result to the RabbitMQ. And the RabbitMQ was used as a message broker to serve multiple different components, including the dashboard that our security department used to see what's in real time, how many empty spots are on the parking, for a smart gate that opens up a gate if there are empty spots, and so on and so forth. And also for sending the data to historical storage for future retraining and so on and so forth. So some practical recommendations that I would recommend you to use for if you are to design a machine learning solution. So first of all, in general, there are many cloud-native solutions and cloud-native patterns that actually significantly help to address many machine learning specific challenges. And the Kubernetes and Dockerized application is a really hot area these days in machine learning because it addresses exactly those problems that we have. It's composability, portability, scalability, and those are quite crucial in machine learning. There are also a number of open source machine learning libraries that help address many different steps in machine learning lifecycle, or are able to even cover the whole machine learning lifecycle for you, so you don't have to create a custom or bespoke new solution once you're starting a new project. Some of these solutions are mature enough to use in production, such as Kubeflow from Google or MLflow. And the last thing is that what we learned personally from our experience, from our project, that it's quite important to keep the tight cooperation between software engineering and machine learning teams, because it used to be two separate worlds, right? So there was a data science team that was working on a model, then they just handed that model to the software engineering team just to deploy it, right? There was no communication, no integration. And we learned that we need to involve the multidisciplinary team into every development step in the project lifecycle in order to actually make it the most efficient and maximize the project success.
So, so as a conclusion, I hope that in this presentation we were able to show you that architecting machine learning systems poses new challenges compared to the development of traditional systems, because of this situation where the behavior is not specified directly in code, but is learned from data. So when architecting the systems that support machine learning, we need to make decisions to considering both workflows. We can just focus on one of the two, initial model development and this continuous model refinement cycle. And hopefully also this framework that we presented can be used as a guideline or provide guidance in designing systems, machine learning systems, in a systematic way. So that is it. So thank you very much.
All right, so I think we have 5 minutes for Q&A.
Yeah, thank you for the talk. So I have a quick question for your first example for the machine learning you delivered for your customer. I see you use a lot of technology like Kafka, Hadoop, CreateDB, Spark. And when you deliver the system to your customer, who will do the daily operation for the whole system? And how much the cost may be? Because we know a lot of technology, sometimes it's not easy to operate all these technologies. So the cost, I'm just curious, is it high, or how you deal with that?
So there's nothing special about that particular project. So you can use the guidance that you have for any sort of big data solution, right? So the cost is more or less the same. The only difference for that project is that some of the components of that system had to be deployed to offshore facilities, and that was quite a challenging part. So that might be quite expensive, but these days we delivered many other different projects to oil and gas companies that operate offshore. These days you hardly ever do any operations offshore. Usually they send the data to the operation center and the data is processed there. But generally speaking, for any given machine learning project, there is nothing specific in terms of the operations. It's rather a type of operation that are new. There's something that, as Humberto mentioned, many of the concerns that we mentioned today, you will never hear them from the client. You should know them before. So that's the challenge.
Okay, one or two more questions.
Oh, there is a question.
At the parking lot project, how did you guys handle the areas that was blocked by like taller vehicles?
You mean for smart parking?
Yes.
So
if you have the camera at this angle and then a truck, parks over here, so the camera cannot see the parking spot behind.
That's a good question, but if you notice on the video, our cameras are located at the rooftop, so they're shooting the parking lot from the top, so there is no way to block it. Well, we played multiple. We played with this angle and the perfect location, and since we are using multiple cameras, right, some of the areas that are hidden or blind for one camera are better seen by another camera.
Okay, one last question. Okay, then let's thank the speakers again.